All right, let's dive in. Today, we're going to talk about something that's all around us, but we barely ever think about concrete. We're going to see how scientists are basically giving this ancient material a crystal ball, teaching it to predict its own future using AI. We're talking about making the very foundation of our world smart.
It all really starts with this one simple question. Every single day, you put your trust in concrete structures. But how can we really be sure they're safe? Not just for today, but for 50 or 100 years from now. The stakes, well, they really couldn't be any higher. So the answer isn't just to pour more and more of it. Nope. The real breakthrough here is about making concrete smarter. And the key to doing that is creating a perfect digital copy, a virtual replica that can live out its entire lifespan in just a matter of hours. So that brings us to our first section, the concrete conundrum. Because for material that seems so simple, right, it's just gray rock, but it's hiding some seriously incredible complexities. I mean, think about it. Concrete is literally the bedrock of our cities. But under that simple surface, it's this chaotic mix of different materials. And trying to predict how it's going to hold up after decades of stress and weather and corrosion, well, that's a massive engineering challenge. Even tiny, tiny changes in the recipe can lead to huge differences in how it performs down the line. So how in the world do you solve a problem that can take a whole lifetime to actually show up? Well, you don't wait. You build a digital twin. You basically create a virtual world to test the future of the real one. Okay, so what is a digital twin? Think of it like a perfect data-driven video game version of a real object, like a bridge beam or a support column. With this twin, engineers can hit fast forward on time, they can simulate earthquakes, they can pile on decades worth of traffic and see exactly what happens, all without risking a single failure in the real world. So how do they actually do it? Well, first up, scientists have to create these super precise physical samples of concrete in the lab. Then they put those samples through the wringer, crushing them, bending them, corroding them to get all that juicy performance data. Next, all of that crucial data gets fed into an AI model to train it. And finally, that AI becomes the brain of the digital twin, ready for all the virtual stress testing you can throw at it. Okay, and this is where the real magic happens. The AI is the digital brain of the whole operation. It does all the heavy lifting, forecasting exactly how that concrete is going to behave over time. Now, to pull this off, engineers use a whole suite of specialized AI tools. You've got things like the finite element method, or FEM, which is basically a physics simulator for predicting how a beam will bend under stress. Then there are artificial neural networks, which are incredible pattern finders that can spot these super complex relationships in the data to model things like shear strength. The point is, each tool has a very specific job, and when they work together, they build an incredibly accurate forecast. But all of these fancy tools, they serve a much bigger purpose, and this quote really hits the nail on the head. It's not just about predicting when something will break. It's about building a framework that connects the tiny, microscopic ingredients in the concrete mix to the huge, macroscopic behavior of an entire building. It's about finally understanding why it behaves the way it does. But hang on a second. An AI model, no matter how smart it is completely useless without high-quality, real-world data to learn from. So you gotta ask, where does all this essential data actually come from? Well, it comes from what we're calling the real-world blueprint. This next part is all about the painstaking physical experiments that make the digital twin not just some cool simulation, but a truly accurate forecasting tool. The answer is really brute force, but guided by science. Researchers literally create and then systematically destroy thousands upon thousands of concrete samples. Every single crack, every fracture, every point of failure, that's a precious data point that makes the AI smarter and the predictions that much more reliable. And they're not just testing one simple thing. The experiments are incredibly broad. You can see a huge focus is on the mix design, the recipe itself. But labs are also meticulously testing all kinds of different reinforcement layouts, the very shape of the concrete parts, and the impact of all these newfangled fibers and additives. And this is where we see some truly mind-blowing innovation. I mean, forget just cement, sand, and water. We're talking about geopolymer concrete that actually uses industrial waste as a building material, or new mixes made from recycled demolition debris. Scientists are even testing incredible additives like graphene oxide and swapping out steel fibers for natural, sustainable ones from plants like sisal. And the results? They're just staggering. Get this. By adding these tiny, almost invisible amounts of graphene oxide and nano-nickel oxide to that concrete made from industrial waste, researchers have seen a 50% increase in compressive strength. That is a massive leap forward. It shows we can build way stronger with smarter, more sustainable materials. Now, it's not just the concrete recipe that's evolving, it's the reinforcement inside of it. Traditional steel rebar is strong, sure, but its mortal enemy is rust. So now engineers are using things like glass fiber reinforced polymer bars that just don't corrode. And they're even mixing tiny microfibers directly into the concrete to control cracking from the inside out. So, what does this all add up to? You put the digital prediction and the physical innovation together, and what do you get? You get a future of smarter, stronger concrete. This is the real-world impact. So here's the payoff. Here's why this matters. We get safer infrastructure. We can predict the kinds of weaknesses that lead to catastrophic failures before they ever happen. We can design more efficient buildings that use less material. We get the confidence to use sustainable and recycled mixes at a huge scale. And we can do smarter maintenance, targeting repairs with surgical precision. It's a total game changer for how we build our world. You know, to really get how big of a deal this is, you just have to look at this timeline. It really wasn't that long ago that all of this was done with manual calculations and slide rules. Then we got basic computer models paired with physical tests. But where we are now, with AI-powered digital twins, it is an absolute quantum leap forward. And the final piece of the puzzle is what they call closing the loop. By embedding sensors, like fiber optics, directly into real structures, bridges, buildings, you name it, we can stream live performance data right back to the digital twin. This means the digital model doesn't just predict the future once, it actually evolves in perfect sync with its real-world twin throughout its entire life. Which, of course, leaves us with one final, pretty wild thought. We've gone from simple prediction to a living, breathing digital copy. So, what's next? Are we on the verge of creating infrastructure that not only monitors its own health, but maybe can even heal itself? The future of concrete might be a lot less about rock and a lot more about intelligence.